All right, in section 5, our last review section, we're going to look at exponential and logarithmic functions. Now, exponential functions is what we'll look at first. And if you recall exponential function, that's going to be any function of the form f of x equals b to the x, where b is greater than 0, but b is not equal to 1. So any number bigger than 0 but not 1, if you raise that to the power of x, you have an exponential function. And the big thing about an exponential function, you're essentially multiplying each time. So let's go ahead and look at a couple other things about these functions. So they have a specific domain and range. The domain of every exponential function is going to be negative infinity to infinity. And the range is generally going to be from 0 to infinity, unless you move the function. So in general, if I have a function, an exponential function is either going to look like this, where it kind of decays and goes down, but it never touches that y-axis. It's kind of like a horizontal asymptote there. Or it's growing. Some of them grow like this and go up. But in either case, you can see it goes from 0 to infinity. Because you can never have a negative number. You can never take a number to a power and get a negative value. Can never get 0 as well. Now, you can move this, you can switch it, you can flip it upside down, and it would change the range. But in general, it goes from 0 to infinity unless you change it. So this horizontal asymptote of the exponential function is something we can find actually from the equation. So if we're given the exponential function, let's call it f of x equals b to the x plus k. So the big thing is this plus k at the end. I'm adding k. Or subtracting, it could be negative. Then the horizontal asymptote is y equal k. So the horizontal line it's going to approach is just going to be y equals k, whatever's added on to that. So we can use this idea and we can just use a couple points to graph these and kind of see what our exponential functions look like. So if we look at a couple examples, this first one, it says state the domain and range in the horizontal asymptote. Well, two of those are really, really simple. The domain is always going to be negative infinity to infinity. So for both of these, I can go ahead and write this. If it's something to an x power, there is no number you can't plug in. Now, the horizontal asymptote, remember we said, is whatever number is added or subtracted to the end. So in this case, it's y equals 2. In this case, the horizontal asymptote is y equals 3. Now, the range is what's going to be a little different in these cases. So let's go ahead and just graph it and see what it looks like. So I have this horizontal asymptote at 2. So I'm going to kind of put a dashed line right here at 2. And it's going to either grow or decay. I don't really know. So what I'm going to do is I'm going to pick a couple points. So for this graph, I'm going to try to make a little table of just a couple points that'll help me guide my graphing. So maybe I pick 0 or 1 or 2. Those are pretty easy ones. So 3 to the 0 plus 2. Remember, anything to the 0 power is 1. So 1 plus 2 is 3. 3 to the 1 is 3. 3 plus 2 is 5. 3 to the second is 9. 9 plus 2 is 11. So I have the point 0, 3, 1, 5, and 2, 11. So since I know the graph has to approach this asymptote, if I kind of see the pattern, it's going to flatten out on the left side versus the right side. So it looks something like this. So now I can use this to figure out my range. My range is going to approach that horizontal asymptote. So it's going to be 2 to infinity, because it's obviously going to grow forever and ever going up. but it's going to approach that 2 as that horizontal asymptote. Now, of course, you can always go to Desmos, look what the graph looks like. That's always an option. It's going to be very similar for this one. The only difference is going to be, you notice the negative in front. So we have a horizontal asymptote of equals 3. And so if I pick a couple points for this one, x and f of x, maybe I pick, I guess it'd be g of x in this case. So say I pick 0. Well, 1/2 to the 0 is 1. With the negative sign in front is -1. -1 plus 3 is 2. So I know I have the point 0, 2. Let's pick, say, 1. So if I pick 1, 1/2 to the 1 is 1/2. So that makes it -1/2. -1/2 plus 3 is 2.5. So at 1, it is at 2.5. So something like this. Let's do a -1. If I do -2, 1/2 to the -2, it will flip it, so it will become -4. -4 plus 3 is -1. And of course, for all these, you could just put the values in your calculator. So this one's going to look like this. It's going to dive down. So it looks kind of like the one over here, except for it's flipped over. And so the range in this case, because it's flipped over, is going to be -infinity to 3. Because the values go down forever, and then their maximum is at the asymptote. That's pretty common when you do the flip with the negative sign. Now, one of the biggest things we do with exponential functions is we introduce the concept of a logarithmic function. Now, a logarithm, if you recall, is basically a way to figure out this exponent in an exponential. So our goal with making a log is it's really a way to express the exponent in terms of the base b and this value y. So if you have some exponential y equals b to the x, then you can convert that to log form by saying x, which is the exponent, equals log, same base, base b, and whatever's on the other side of the equal sign now becomes your input of your logarithm. So the logarithm is a rearrangement of the exponential function to get the exponent by itself. So they are inverses, so all the inverse properties we know can work. So if you look at some of these, this first set is in log and the second one are in exponential. You can switch freely back and forth between them. So if I have the log 16 of 256 equal 2, exponentially that is 16 to the second equals 256, just using this pattern from up here. Log base 12 of 144 equal 2 is saying what 12 to what power is 144? Well, 12 to the second is 144. Same thing here, it's saying 81 to what power is 9? So it's 81 to the half power is 9. For fractions as well, log base 6 of 136 equals -2. That's 6 to the -2 equals 136. So in this case, I'm taking this side and I'm converting it to look something like this. Log base 4 of 1 equals 0 will simply be 4 to the 0 equal 1. And log base 2 of 8 to the third can be rewritten as 2 to the third equals 8. So sometimes rewriting a log in terms of an exponential can make life easier. Now in this case, all the numbers were given, so it really doesn't matter which way you write it. But in the future, when you have some variables, that can make a difference. So if we look down here, we have things in exponential, so we're going to turn them to log. So remember, the whole purpose is to get this exponent by itself. So you can rewrite this as -2 equals log base 6 of 136. Because the base of the exponential remains the base of the log, and then your input value goes on the other side. So again, the goal is to get the exponent by itself. So 2 equals log base 7 of 49. 5 equals log base 2 of 32. 3 equals log base 4 of 64. And finally, -4 equals log base 5 of 1 over 625. So this basis of a logarithm is really, really nice, really easy to use. And we will use it in the future. We'll use it to actually graph our log functions, and we'll also use it to solve some exponential and log equations, which is one of the biggest things we will use in calculus. So when we're defining logarithmic functions, the logarithmic function is generally going to be any function in the form, and I'm going to write it this way: y equals log base b of x, where b is greater than 0 and not equal to 1. Or if we use the thing we talked about before, this log and exponential form, y equals log base b of x is the same as saying b to the y equals x. So if I convert it to exponential form, it's the same thing. So a log relation, again, with the y by itself becomes the y of the exponential. And this is important because it's actually much easier to graph the second thing than it is the first thing. Now, domain and range get switched for a logarithmic function because they are inverses. So that's going to mean the range is always negative infinity to infinity for a log function, nothing changing. And the domain is going to become 0 to infinity unless we change where it starts. Just like you could change the horizontal asymptote and change the range for an exponential, we can change the domain for a log. Every log function will have a vertical asymptote. So we can say for a function, for a log function, I'm going to write it as log y equals log base b of x minus c has a vertical asymptote at x equals c. So again, it's inside the function, so it's basically the opposite of the sign you see. So if it's a minus sign in there, it becomes a positive vertical asymptote. If it's a positive, it becomes a negative. Now, in general, if there's nothing inside the parentheses, we just consider it 0. So when we look at these two functions, the graph of log of x and the graph of log base 2 of x minus 1, there's nothing in it. So for both of these, they're just going to have vertical asymptotes of 0. We also know the range for both. Range is going to be negative infinity to infinity because every log function has that for its range. And the domain, it doesn't change because there's no change in the vertical asymptote, so it should be 0 to infinity for both. Now, this doesn't tell me a lot on how to graph these functions. All it really does is tell me, all right, this has a vertical asymptote here, and this has a vertical asymptote here. So I'm going to rewrite this as y equals log of x. Now, there's no base, so remember, if there's no base, it's 10, unless it's an ln, and then it's the base of e. Well, if I rewrite this in exponential, it's 10 to the y equals x. So a really, really easy way to graph these is instead of picking the x values like we typically do, if we pick some y values like 1, like 0, like -1, then what we can do thus is find the x value for that. So if I put the y values into my rewritten log, 10 to the first power is 10. So I get a power of 10(1), which is right there. If I do 0, I get 1, so that's 1, 0. And if I do -1, 10 to the -1 is 0.1. So really, really, really small. So a log will typically look like an exponential just going the other direction. So it's going to look something like this. So if you go to your Desmos calculator or something like that and type in log of x, you should get a graph that looks something like this. Same thing for this one. So we can have y equals log base 2 of x minus 1. So if I want to solve that, I could add 1. So y plus 1 equals log base 2 of x. And then I can convert it to log form. So it's 2 to the y plus 1 equals x. And so it's the same concept. We have x and y. We have I'll do -1 for y and 0 and 1. So if I do -1, that gives me 2 to the 0, which is 1. So we have -1, or 1 and -1, which is right there. If I do 0, I have 2 to the first, which is just 2. So that's 2, 0, which is right there. So you can kind of see the same kind of graph occurring. If I do 1, it's 2 to the 2, which is 4. So 4 to the 1. So you can kind of look at your log graph. It looks like this. So they both have basically the same shape. You can see this one's a little flatter because it's got a base of 10. This one's a little more, rise a little upwards because it's a base of 2. But in general, switching it to these exponential forms is the easier way to deal with these logs. So the last thing we're going to look at is solving these exponential and logarithmic equations. And exponential and logarithmic equations essentially are going to be, an exponential is going to be an equation with the variable in the exponent. And a logarithmic equation is simply going to be an equation with a log in it, with a log term. So one of the biggest ways we're going to solve these is doing our switching of forms. So like we talked about, b to the x equal y is the equivalent of x equals log base b of y, where the exponent goes by itself. We'll also take advantage of some of our old log properties. So if you remember the log properties, we have the log x plus log y equals log of xy. The log of x minus log y is the log of x divided by y. And then we have n log x can be written as log of x to the n. These are all pretty important log properties that you learned before. We will use these, maybe not so much in these problems, maybe on a couple of them, but we'll definitely use them throughout the course. So if we're trying to solve these, find the exact solution, and then the approximate solutions, of course, just putting in your calculator. Let's go ahead and look at this first one. It is 3 to the x minus 2 equals 7. So it's in exponential form, so I'm just going to simply switch it. So the exponent, which is x minus 2, will become the log base 3 of 7. Now the log base 3 of 7 is some number, so that's good. And so all we have to do now is get the x by itself, so we'll just add 2. So x in this case is going to be 2 plus log base 3 of 7. That is the exact answer. Now, if you want to put that into a calculator, get your approximate solution, you certainly can. But when we're talking about exact solutions, that is a number. Let's look at this one over here. Similar to the other one, it's a pretty basic equation, except for this one's in log form. So I'm going to try to change it to exponential. So again, the base of the log is the same as the base of the exponential. In log form, the exponent's by itself, so you have the 3 here equals 2x plus 4. So I'm just switching forms. And the nice thing about this one is 3 to the third is 27 equals 2x plus 4. And I just solve from here. So we'll subtract 4 from both sides. I'll get 23 equals 2x. Dividing both sides by 2, x is going to be 23 over 2. So this one again, this one is a kind of a similar problem, although we have to play around with it a little bit because it's not really an exponential form, it's not really in log form, it's some kind of intermediate form. So what I'm going to do is I'm going to add 4 to both sides first. So I'll get 3 e to the 2x equals 5. And e, remember, is just some number. I'll divide both sides by 3. So we get e to the 2x equals 5/3. So now it's an exponential form because it's a base number to an exponent equals a number. So we'll change it to log form. So we have 2x, and now it would be log base e, because e is the base there. So if you remember, we use ln. ln is a natural log. It automatically has a base of e. So ln of 5/3. So I don't have to write the e when I write ln. We are assuming it is a logarithm that has a base of e. ln and e are really, really important in calculus. We will try to do most of our stuff with e and ln. And we'll just simply divide by 2. So x is going to be ln of 5/3 over 2. That is my exact answer. Now the final one here is a little tricky. It has 2 log terms, and it has a 2 there. So what I'll have to do is when you have multiple logs and you're trying to solve, we have to basically put them together. So I will add log base 2 of x to both sides to get them on the same side. So I have log base 2 of x plus 3 plus log base 2 of x equals 2. So this is going to go to one of those properties we talked about from above. It said when you have 2 logs that are added together, I can write that as a single log of the 2 things in parentheses multiplied. So you can write this as log base 2 of x times x plus 3 equals 2. So that takes advantage of one of those properties where you're taking 2 logs and you're combining it to 1. So now we can simply finish up just by turning to exponential. So it'll be 2 to the second equal x plus 3. So that's 4 equals x squared plus 3x. Now, unfortunately for this, it's a square, so we'll have to solve it like a quadratic. So I'll get everything on one side. So we'll get 0 equals x squared plus 3x minus 4. And then I'll factor it from there. Or you could do quadratic formula. However you want to solve this quadratic is fine. So the 2 factors, 2 numbers that multiply to negative 4 add to 3 are plus 4 and minus 1. So that's going to mean x is equal to negative 4 or positive 1. Now that would seem like fine answers, but there is one issue. Do you remember when we said that log has a domain of 0 to infinity? It's only positive numbers. So I cannot have negative 4 as a solution, because if I were to check that in the problem, I would be doing the log of negative 4, which is out of the domain, so it does not exist. So just some simple log and exponential equations. We will solve quite a few of these, so it's always a good idea to go back and review them. If you do have any questions about these, obviously, please let me know.